Okay, let's get started.
Okay. Hello, everyone. Today we will present our mini project. We are group BJL, including Boeing, Jie, myself, Lianhe. And first, about the content of our presentation. It included the introduction, data sets, K-fold, pre-process, models, results, and summary. Next, please. First, about the introduction, here we did analyze 21 datasets from the 121 UCI datasets. We did performed extensive set of experimenting and evaluated performance. And to aim for the grade 5, we developed and evaluated 3 unsupervised and 3 supervised classification models. And we pasted the link of our original code here as well. Next, please. So here are the 21 data sets for binary classification. And we know that the number of participants information included here, and also the features, classes, and the majority accounts also provided here. And there are different data sets, including the Congress voting, magic and blood, and the fertility, and also some, for example, disease such as breast cancers and so on. Yeah, next please. And then we inspect the data sets, including the number of data instances, the data set, whether the data set is balanced or not, and the number of features, the feature types, is it categorical or numerical data set. And we also checked whether the any missing values. Yeah, next please. And here, in order to use a more reliable performance for estimation, we use the 4 cross validation instead of splitting the dataset into train and test the dataset. And the K for the cross validation split the data into K subsets and uses each subset as a test set while training on the remaining K1 folders. This process is repeated K times, and the performance metrics are averaged. And this leads to a more reliable estimation of model's performance, since it considers the multiple train test splits. And also to make sure a better use of data with a single train test split, some data may not be used either in the training or testing phase. K-fold cross validation ensures that every data point is used for both training and testing. That's to maximize the use of average data. And also we have provided a pre-process pipeline diagram here to sequentially apply a list of transformers to pre-process data to deal with missing values. For categorical features, we use the most frequent to input the value. And for numeric features, we use mean to input the values. Then one hot encoder is applied to categorical features and the numeric values as they normalized. And but here we needed to be noted that the statistics, including the mean and the standard deviation, are from the train folder. And the test folder uses the train folder statistics to do the normalization to avoid the data leakage.
Yes, so for the models, we have used 3 supervised learning models and 3 unsupervised learning models. KNN, SVM, random forest, and then for unsupervised learning, we use K-means, BIRCH, mean shift. They are implemented with scikit-learn. Um, yes, and here follows the result of our supervised learning models. Here is an overview of the accuracy of the 21 datasets with 3 supervised learning models. And yes, the blue bars are for KNN, the orange is for the random forest, and the green is for SVC. And the accuracy measures the proportion of correct predictions out of all predictions. But it can be misleading if the classes are imbalanced. So that's why we also check the recall and precision and also F1 score of the datasets. Yeah, then followed the precision of the 21 datasets. Precision measures the proportion of the true positive predictions out of all positive predictions. Precision is very important when the cost of false positive is high. And for recall, recall is also known as sensitivity or true positive rate. It measures the proportions of true positive prediction out of all actual positive instances. Recall is important when the cost of false negative is high. And here is the F1 score of the datasets. F1 score is the harmonic mean of precision and recall. It provides a single metric that balances both precision and recall. The F1 score is very useful when we have to balance the precision and recall when we have an imbalanced dataset. Then in order to have a general impression which classifier is generally performs good, then we do a summary or average of all 21 datasets for different classifiers. Here in this table, we see that random forest in general outperforms KNN and SVC in terms of accuracy, precision, recall, and F1 score. Then it comes to the unsupervised learning models performance. Here in this figure, we show the homogeneity of the 21 datasets. Homogeneity measures whether all clusters contain only data points that are members of a single class. The homogeneity score close to 1 is better. It means that each cluster contains only one class, while 0 means there's no homogeneity. And we also check the rand index of the datasets. Rand index evaluates the similarity between two data clusterings by considering all pairs of samples and counting pairs that are either correctly clustered together or correctly not clustered together. Another performance metric is completeness. Completeness measures whether all data points that are members of a given class are assigned to the same cluster. So a score 1 means that all data points of a class are in the same cluster, and 0 means there is no completeness. And V measure, it is the harmonic mean of homogeneity and completeness. It balances both homogeneity and completeness, ensuring a more robust evaluation. And here in this slide, we also show the average of the all 21 datasets. And in general, K-means performs better than Birch and mean shift.
Yeah, compared, we now we also compare the result with the paper's result. So we list the data sets of first 10, and we have used the supervised learning with KNN, random forest, and the support vector machine. And we compare with the paper that is in the blue column, that is KNN caret, parallel random forest, and support vector machine. Yeah, the next page is the continued data set. And we can see we also see the average value for the KNN method with our result KNN, and the paper result KNN caret 85%, and the random forest 87.8%, and the parallel random forest in the paper 86%, and support vector machine of our result is 87%, while the support vector machine in paper is also 87%. And the paper mentioned the parallel random forest method is implemented in R, and with the caret that achieved the best result. And we can see our average value are comparable with the paper results. Yes, so here we comes to the summary. Supervised both we have evaluated the supervised models and unsupervised models, and we have re-evaluated them separately. And of course, we can manually assign labels to clusters by examining the majority class of the data points within each cluster, and then evaluate the accuracy for the unsupervised models. But we think it makes more sense to evaluate them separately with different matrix, as we have mentioned before. And our results are comparable with the benchmark results that are shown from the paper. And from our experiments, the supervised models and in supervised models, the random forest performs generally better than the support vector machine and the KNN. And for unsupervised models, the k-means performs generally better than Birch and the mean shift. And we also have some doubts about the paper. In the paper, section 3, results and discussion, the validation methodology, the dataset is split into 50% as train and test, another 50% as test for parameter tuning, and then use the whole dataset and tune the hyperparameters to do the fourfold cross-validation as the test result. We think it will lead to data leakage. And also we noticed the wrong metadata for the chess dataset. It should be 36 features plus one label. But in the metadata, the 36 feature is pre-processed as the label. And another minor suggestion for the paper, and the naming of the data sets presented in the paper are not consistent with the benchmark result, which makes us difficult to find the correct alignment. Yes. And this is the reference paper that we have used in our project. Yeah, I think with this, we will conclude our presentation. Thank you.
Thank you.